Good day and welcome to our topic 4, that is part of our module 1 on our antimicrobial lecture series as part of our basic level training on antimicrobial resistance. So in this part 4, we are going to discuss inhibitors of protein synthesis. We're going to discuss inhibitors of protein synthesis. Okay, so protein synthesis inhibitors. Now, like all life on Earth, bacteria synthesize proteins for their structural and functional needs. So we all need proteins so that we can survive, and bacteria also do the same. So they also try to synthesize proteins so that they can use, okay, for their structural and functional need. So an organism cannot survive without making proteins because all life is built from that scaffolding of proteins. Okay. Then protein synthesis is a multi-step process where we first have DNA that is transcribed into a molecule of a single-stranded messenger RNA, So we have a DNA that is transcribed to a single-strand RNA, and that RNA is a messenger RNA. It's a messenger RNA. So then from them, ribosomes translate it with the help of transfer RNA into a long strip, into a long strings of amino acid, which then becomes proteins. So protein synthesis inhibitors prevent proteins from being made by acting as inhibitors of translation or transcription. So those are the agents that prevent proteins from being made. So here we can see a DNA, a double-strand DNA, and from this DNA here, we can see that a single-strand RNA is being synthesized. So this is the initial phase that we call transcription. So during this phase of transcription, a copy of a DNA is made as a single strand of a messenger RNA. So the messenger RNA will then take the information to the transfer RNA, informing the transfer RNA what type of amino acid that can be brought for the formation of the proteins, the specific proteins that is required. Okay, so here we can see we have the translation stage where the messenger RNA attach here to the ribosome, send the information to the transfer RNA, and during this translation, so actually the messenger RNA bind to the ribosome, and transfer RNA brings amino acid to build the proteins that is required to build the protein that is required. Okay. So antibiotics that target protein synthesis, we have several classes of antibiotics that inhibit protein synthesis in bacteria by interfering with the 70S ribosome or its different subunits. Remember, the bacterial ribosome has 30S and 50 subunits, but when they are combined on a single complex, they are 70S ribosome. So antibiotics that interfere with bacterial growth or reproduction are called bacteriostatic, and those that killed are called bactericidal. So those concepts, we discussed them during our first topic. So if you missed the first topic, you can go back and look at them. So here we can see This is the ribosome with of bacterial ribosome with the 2 subunits, the 30S subunit and the 50S subunit. And we can see here the inhibitors of protein synthesis that target specific subunit, like the smallest subunit here is the 30th subunit. We can have here spectinomycin that has a target here on the 30th, tetracycline, we can see streptomycin, we can see all those, aminoglycoside, they target the 30S subunit of the bacterial ribosome. And the 50S, we can have streptogrammin, we have chloramphenicol, we have lencosamine, we have macrolide. Those have targets, on the 50S subunit of the ribosome. So let's first look a bit with more details, those that antibiotic that act on 30S ribosomal subunit. Okay, so we start with aminoglycoside. Aminoglycoside, we know from our topic 1 that they are bactericidal, they have bactericidal activity, and we know that they include drugs like streptomycin, kanamycin, gentamycin, tobramycin, amikacin, neomycin, and so on. Okay, and their mode of action is that the aminoglycoside irreversibly binds to the 16S ribosomal RNA, And by doing so, they freeze the 30S initiation complex. Remember, protein synthesis moves into stages. There is the initiation phase where actually the drug, we have the 30S it happens on the 30S subunit, where the messenger RNA carries the information about the protein to be produced or synthesized, then send the information to the transfer RNA. So there is what we call the 30S initiation complex that is made of 30S subunit, messenger RNA, and the transfer RNA. Together they form a complex. So it's from that complex that the translation will now take place. So what we call the elongation phase. So now, if the aminoglycoside bind to the 30S and freeze the 30S initiation complex, so no further initiation can occur. So they also slow down protein synthesis that has already been initiated. Anything that they have found that was already initiated, they also interfere with that. So by inducing misreading, of the messenger RNA, so they create misreading of the messenger RNA, the information that the messenger RNA will bring to the transfer RNA will be misread, and wrong amino acid will be brought for the formation of wrong proteins. So by binding to the 16S ribosomal RNA, the aminoglycoside also increase the affinity of the A site, for the transfer RNA, regardless of the anticodon specificity. So this is actually what happened. And in terms of spectrum of activity of aminoglycoside, we know that they largely interfere with gram-negative bacteria, and and they are not really useful for anaerobic bacteria because oxygen is required for the uptake of these antibiotics, and they really are not useful, or they cannot be used against intracellular bacteria. And they are commonly used with in combination with beta-lactam antibiotics, because then beta-lactams will inhibit the cell wall synthesis, allowing aminoglycosides to penetrate to the cell to go and inhibit the protein synthesis. Beside the aminoglycoside that act on the 30S subunits of the bacterial ribosome, we also have the tetracycline. And tetracycline have a bacteriostatic activity. And here we have the tetracycline, we have the minocycline, we have the doxycycline that belong to this category of drugs. And according to their mode of action, the tetracycline reversibly, remember aminoglycoside we say irreversibly bind, but tetracycline reversibly binds to the 30S ribosome and inhibit binding of amino acid tRNA to the acceptor site, on the 70S ribosome. So they are broad spectrum, they have a very broad spectrum activity, and they are also useful against intracellular bacteria. We also have a spectinomycin. Usually people, although spectinomycin have a structure that is almost looking like a aminoglycoside, but here you can understand that spectinomycin are sometimes wrongly classified as aminoglycoside. So they are not aminoglycoside. And the spectinomycin irreversibly interfere with messenger RNA interaction with the 30S ribosome. So its structure, we say it's similar to the aminoglycoside, but it does not cause misreading of messenger RNA like it does aminoglycoside. Okay, so its spectrum of activity, it's used in the treatment of penicillin-resistant Neisseria gonorrhea. And in some parts of the world, it is still a treatment of choice for treating Neisseria gonorrhea. But because the MIC has been increasing to the right, the use of spectinomycin has been reduced because we have now cases of resistance. And the other group of protein synthesis inhibitors, we have those that bind to the 50S ribosomal subunit. And here we have the group of chloramphenicol, we have vancomycin, we have clindamycin. And those drugs have a bacteriostatic activity, like your clindamycin. So the mode of action is that this antimicrobial agent bind to the 50S ribosome and inhibit the peptidyl transferase activity. So they interfere with the activity of the enzyme called the peptidyl transferase. Okay, chloramphenicol has a broad spectrum activity, but vancomycin and clindamycin are very restricted mainly to your gram-positive bacteria. We also have the macrolide that they also have a bacteriostatic activity. And in this group, we can have your erythromycin, clarithromycin, azithromycin, and spiramycin. So the macrolides inhibit the translocation phase, and they are very good against gram-positive bacteria, and especially intracellular bacteria like mycoplasma. And they also have a better activity against Legionella. Then we have a fusidic acid. That fusidic acid binds to the elongation factor G and inhibits release of EFG from EFG GDP complex. So fusidic acid is good against gram-positive. So to summarize this, during the initiation process of protein synthesis, the initiation phase, we have drugs that act on the 30S subunit here because it's where the initiation takes place. And here we have a spectinomycin that inhibits the formation of the 30S initiation complex here. So it does not even happen. And we have the spectinomycin inhibit the messenger RNA. So the complex, the 30S complex will not even be formed. And the aminoglycoside frees this complex, 30S initiation complex is completely frozen by the activity of the aminoglycoside. And we also remember that the aminoglycoside causes misreading of the information brought by the messenger RNA. Okay. Then on the elongation phase, we have the tetracycline that acts here, and we have the chloramphenicol this side, the erythromycin, and the fusidic acid, although they all act on the 50S ribosomal subunit, but they still interfere at different phases, at different sites of the elongation phase of protein synthesis. Okay, so let's try to look at his assessment, on test 1, a patient comes into the hospital with a severe intestinal infection. She says she is a technician in a biology lab that works with gram-negative bacterium, Shigella flexneri, which causes dysentery. So we know that this patient is a technician in a lab, and he is mainly involved in a work, that deals mainly with Shigella flexneri. And Shigella flexneri is a pathogen that causes dysentery. At the moment, the hospital has run out of all antibiotics. This is a situation that we see often in developing countries. In some of those countries, sometimes they run out of medications, and even in some countries, even if they have money to buy those medication on time, but they are faced with challenges about procurement, and supply chain is not working appropriately, and they end up running out of some certain drugs. Now they remain only with protein synthesis inhibitors, and the question is, which of these drugs would not be a good choice to be given to this patient? So pause your video for 30 seconds and try to respond to this question. Okay, so we can see that against gram-negative, your choice will not be oxazolidine because Shigella flexneri, and streptomycin is also not really a good choice for this condition. But tetracycline can be used, against Shigella flexneri. But what you need to understand is mainly the epidemiology of antimicrobial resistance in your setting, because we have quite high cases of resistance of Shigella to tetracycline. So you need to understand your local epidemiology. So the good choice here could have been if you had your fluoroquinolones, if you had your third generation cephalosporin, those could have been better choices. But since you don't have them, you can use tetracycline. But as we said, you need also to understand the local epidemiology in terms of antimicrobial resistance to support your choice. The second test is Which of the following protein synthesis inhibitors have a wide spectrum of activity, and its site is of inhibition of 50S? Okay, so this one inhibits 50S subunit of the ribosome. I think we need to try to exclude those that do not, like your tetracycline, aminoglycoside, they don't act on the 50S. We know that they act on the 30S, so you can remove them. And we know that clindamycin does not have a wide spectrum of activity because clindamycin acts primarily on gram-positive bacteria. And the linezolid also does not have a broad spectrum activity. So the answer will be A, chloramphenicol. So your answer will be chloramphenicol. Okay, so follow us on the topic 5, that is about inhibitors of nucleic acid synthesis that we are going to discuss. Thank you.